Students, I'm going to talk to you about a sport that seems unusual, but this is going to be a example problem. Um, so this is the sport. We take a bowling pin. Bowling pins weigh about 1.5 kilograms. We put it on a tabletop, and then we shoot a bullet at it. Bullets are about 10 grams. That's close enough. All right, we're going to shoot it with some velocity v, which if you'll give me a moment, I'll figure out what I want. All right, so we're going to allow this projectile to move at 300 meters a second, and we're going to shoot it into this bowling pin, and then it's going to fly out the other side with some final velocity. And the bowling pin is also going to move. A little bit later, it'll be like that. It'll be off over there. It'll have some velocity as well. So there's my, oh, it's moving. Yay, it's moving. So when it's in, all right, so you have some problems like this in the homework is when the projectile goes into the bowling pin, then that's an inelastic collision. They're stuck together. So we can try to figure out what's going on in here. How fast is the bowling pin bullet system moving while they're stuck together? So now this thing will change. This is actually what we're going to call V final, but there'll be some intermediate state where it's moving a little faster. And so what happens first, the collision, right? Well, we have this thing has some momentum, and so M1 V1 initial plus M2 V2 initial. Then this thing has some common velocity equals M1 plus M2 V final, or V, I want to call it intermediate. Let's just call it V. Right. So this stuff's pretty easy. This term is 0 because V2 initial is 0. Hopefully you're not playing any sort of target practice where the bowling pin is moving. And so this term is 0.01 kilograms times 300 meters per second, which is 3 kilogram meter per second. That equals 1.51 kilograms, that's the total mass, times V. Well, that's going to be just under 2. 3 divided by 1.51 is going to be, V is 1.98675, dot, 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 dot. We're going to keep a lot of sig figs, meters per second. And then we're going to ask now, the second part is the explosion. All right, so what happens in the collision is you start out with your projectile and your bowling pin, and they turn into let's see, I'm trying to draw a bowling pin with a projectile in it. So now our explosion is going to be the bowling pin with the projectile turning into the lump of stuff plus the projectile leaving. Right? So when it's all together, it has M1 plus M2 V, and that's going to equal M1 V1 final plus M2 V2 final. Well, this thing we know because it comes from this. It's 3 kilogram meter per second. It's this number times that number. But we don't know everything over here. And that's our problem. See, you need to notice when we kind of get things stuck. And here, we're missing too much information. But, the only way we can go about it is to write the problem correctly. Let's give it a final, let's say it's 280 meters per second. So that's going to be, let's see, what did we call M1? M1 was the projectile. So 0.01 kilograms times 280 meters per second plus 1.5 kilograms times V, final. And now we can solve. This thing is 2.8 kilogram meter per second plus 1.5 kilograms times V, final. So what we have is 0.2 kilogram meter per second is 1.5 kilograms times V, final. And then so we calculate what that is. It is V final is 0.133 ... meters per second. So we can look at this for a minute and realize that we're talking about shooting a relatively lightweight object, a bowling pin, something that's just a kilogram. And we're using, a very light projectile going very fast. And what you kind of see is it doesn't really affect the relatively heavier bowling pin. It gives it a little bit of velocity, but it gives it more of it while they're stuck together. Right? But you can also look at this and you can say, well, what happens if I scale the mass up? Well, if I scale the mass up here, right, the bowling pin doesn't affect this side of it. I get the same momentum no matter what. But it affects this side. So if I scale the mass up, that means the velocity goes down. And the same thing happens here. If I scale the mass of the bowling pin up, the velocity that it has at the end goes down. And there's, that's effectively, that's, doesn't matter what the object is, the more mass of it is, the less impulse that this term can give it. And so if you've ever seen an action movie, right, people get shot and they just go flying like 100 meters. And it's kind of ludicrous in a sense, right? So, the gist of it is lots of different problems we can deal with. We can deal with in terms of sort of breaking it down into, well, something gets stuck with something else. That's an inelastic collision. And we can deal with it in terms of, the inelastic collisions just means that they move with a common velocity. So we can simplify this side. An explosion means they start out with a common velocity and then they spread out. So let's do some other examples.